Everyone knows the quadratic formula. If you're given ax squared plus bx plus c equals 0, we know that x is going to be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. But did you know that there's actually also a cubic formula? If we are given ax cubed plus bx squared plus cx plus d equals 0, we can reduce this to a form like this, where we have y cubed plus py plus q is equal to 0, and then get solutions for y, which will be the cube root of negative q over 2 plus the square root q squared over 4 plus p cubed over 27, all nested like this, and then another plus the cube root of negative q over 2, now it's minus the square root of q squared over 4 plus p cubed over 27, and nested like so. And y is actually equal to x plus b over 3a, which means that we can get x from y minus b over 3a. So the cubic formula is actually a massive milestone for the history of mathematics. It's not often taught. Obviously, this form is a little bit bulkier, but this is best we can get for the fact that we transform it into this simpler form. If you do it directly from A, B, C, and D, the regular form, it's going to be much larger. This one is a little bit easier to memorize that we have here in terms of yp and q. But then also the fact that the way that it gives solutions in this form is also a little bit more complicated. But anyways, we're going to investigate this, do a derivation of it, understand the intuition, where it comes from, and then examples for each of the cases with a discriminant. Okay, so if you know about the way that the quadratic formula is derived, you basically have to complete the square on one side, and then you can rearrange to solve for x. And you might be thinking, hey, how about if there's a way to complete the cube for a cubic? So if you have u plus v cubed, expanding with the binomial theorem, or just simply perfect cube expansion, you're going to have u cubed plus 3u squared v plus 3uv squared plus v cubed. Now we could mess around with this, but it's actually much harder than you might think to kind of find a way to complete the cube in a sort of fashion or manner as seen in the derivation of the quadratic formula. So this won't really help us right now. We're gonna keep in mind that it's gonna be a hint for later, basically. But anyways, let's go and just look at the general cubic. If we have ax cubed plus bx squared plus cx plus d is equal to 0, we like having a leading coefficient of 1, so let's divide everything by a. We're going to get x cubed plus b over ax squared plus c over ax plus d over a is equal to 0. Now, the fact that the center of the graph, or the inflection point, is kind of arbitrary to us can be very annoying to solve the cubic. So how about if there was a way to reduce into a simpler form where, say, the graph is centered on the y-axis, basically the point of inflection would be 0. So the point of inflection of a cubic is actually negative b over 3a. You might have seen that from before at the beginning. If you didn't know this, there is a quick way to derive it from calculus. Basically, the second derivative has to equal 0, and you're going to find that. But anyways, what we're going to want to do, if it's x minus b over 3a, we are going to add b over 3a to basically cancel that, make it 0. So then you're going to see that the x squared term is going to cancel out. So I'm gonna let this equal y, since this is not the actual pure x intercept here. We're gonna get y equal to x plus b over 3a, and then then this means that x is equal to y minus b over 3a. Now we're going to sub these in. So we're going to have y minus b over 3a cubed plus b over a y minus b over 3a squared plus c over a y minus b over 3a plus d over a is equal to 0. Now we're going to expand each kind of grouping of the y minus b over 3a to the n. So first, this cube, we're going to expand it using the perfect cube expansion. We're going to have y cubed minus by squared over a plus b squared y over 3a squared, and then minus b cubed over 27a cubed. Okay, so that's this term right here. Now we're going to move on to the one with the coefficient b over a. So we have plus b over a, expand the square here, the perfect square. We're going to have y squared minus 2by over 3a plus b squared over 9a squared. Okay, and then the c over a term, so plus c over a, well, we're just gonna, this is kind of just left alone, it's only coefficient of 1, so yeah, y minus b over 3a, we're gonna expand it after, and then plus d over a is equal to 0. Now here we're going to want to distribute, we're going to want to distribute these coefficients around and see if we can cancel things out for this. So what we're going to get is, so y cubed still here minus by squared over a plus b squared y over 3a squared minus b cubed over 27a cubed. And then you're going to see here we're going to have by squared plus by squared over a. So here, this is where we can cancel out the squared term. And now keep on going over here. We're going to have minus 2by over 3a, and then plus b squared. Actually, I'm going to make this over 27a squared, because you see we have this over here. We're going to basically add those up after, but I'm going to do it as, keep it as plus 3b cubed over 27a cubed, and then plus cy over a minus bc over 3a squared plus d over a is equal to 0. Now we can simplify things some more. We're going to have y cubed. I'm going to separate these into their terms now. Here now, we're going to have plus, put these in brackets, cy over a plus b squared y over 3a squared minus 2b squared y over 3a squared. Then this next part, so see here I have all the factors with y in there. Now here these are going to be the rest of the basically constants. Negative b cubed over 27a cubed plus 3b cubed over 27a cubed. See that there? And then minus bc over 3a squared plus d over a equals 0. Now, from this term over here, we can basically factor out a y. So we're going to have y cubed plus c over a minus b squared over 3a squared times y plus 2b cubed over 27a cubed minus bc over 3a squared plus d over a is equal to 0. Now this is where we get the p and q from where you saw at the beginning, so here we have y cubed plus py and then plus q equal to 0. So this is our simpler cubic. It is so it's centered exactly on the y-axis, and so we're gonna way to solve this. Okay, now that we have it in this simpler form, what we're gonna be able to see, so we have y cubed plus py plus q is equal to 0. If we come back to our perfect cube formula, what we had over there is, so u plus v cubed is equal to u cubed plus 3u squared v plus 3uv squared plus v cubed. These two terms over here, we can factor out a 3uv. So what we're going to get is u plus v cubed is equal to u cubed plus 3uv u plus v plus v cubed. Now from here, subtract everything to one side. We're going to have u plus v cubed minus 3uv u plus v, and then these are going to be grouped together, the u cubed plus v cubed. We're going to have minus u cubed plus v cubed is equal to 0. And what we can see here is that this y pairs up with the u plus v, this p pairs up with the minus 3uv, again the y with the u plus v, and then the q pairs up with this over here. So if we can find u and v in this form according to our simplified cubic, then that means that it will actually be a perfect cube after all, and so we can properly solve it. So from here we're going to get a systems of equations to work with. So we know that y is going to be equal to u plus v. Then we know that p is going to be equal to -3 times uv, and then q is going to be equal to -u cubed plus v cubed. And these I'm gonna rearrange it a little bit more to make it nicer. We're gonna have uv is equal to -p/3, and then here we're going to have u cubed plus v cubed is equal to -q. And so basically this is our system to work with. We can actually kind of leave this one out, since this is just the sum after we find u and v from here. So technically we only have these two. But anyways, now, so what we're going to want to do, I'm going to label these actually. This is our equation 1, this is our equation 2. What we're going to want to do is, so we're going to cube equation 1, okay? So then we're going to get u cubed v cubed is equal to minus p/3 cubed, okay? Then we're going to multiply the second equation. We're going to multiply it by u cubed, okay? So we're going to have is u cubed squared plus u cubed v cubed is equal to -q times u cubed. And we can see here that we have u cubed v cubed like in the first one, so we can basically substitute that in. All right, we're going to have, so yeah, sub u cubed v cubed is equal to -p/3 cubed in equation 2. Alright, so yeah, now we're going to have u cubed squared minus p/3 cubed is equal to -q times u cubed. Then we can rearrange everything to one side. So we're going to have u cubed squared minus, or sorry, let's do it this way, yeah. In quarter of u cubed, u cubed minus p/3 cubed is equal to 0. And so we can see that we have a quadratic formula in terms of u cubed, or yeah, a quadratic in terms of u cubed, which we can solve using the quadratic formula. So what we're going to get is u cubed, I'm going to, again, after simplifying, what you're going to get is u cubed is going to be equal to -q/2 plus or minus the square root q squared over 4 plus p cubed over 27, right? And then we can take the cube root, so that we get u is equal to the cube root of -q/2 plus or minus the square root of q squared over 4 plus p cubed over 27, right? Okay, and what you're actually going to see is that if you also wanted to solve for v in this way, you're going to get the same thing. So this is also the expression. This is also the expression for v. So now we have y is equal to u plus v, right? And so there's three combinations that we can have, okay? So we have case one. What we're going to have is the plus minus in here, both of them are going to be plus. So we're going to have cube root of negative q over 2 plus blah blah blah, and then plus cube root of negative q over 2 plus blah blah blah, like so. Then there's the second case. The plus minus that's nested inside, it's going to be all negative, so we're going to have the cube root of negative q over 2 minus blah 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 plus the cube root of negative q over 2 minus blah 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 here. And then the last one, the last case is going to be where the plus or minus are opposites here. So you're going to have the cube root negative q over 2 plus blah blah blah, and then plus the cube root of negative q over 2 minus blah blah blah. And this would be the same, same if swapped, right? Because all we're doing here is adding them. And what you're actually going to see if you sub these back into the original simplified depressed cubic, what you're going to see is that this is the only valid, the only one that provides valid solutions. So now what we're going to want to do, talk about the discriminant, okay? So the discriminant is what's inside the cube root, inside of the square root, the nested roots. It's going to be the q squared over 4 plus p cubed over 27, and we're gonna check various equalities to 0 basically. So the first case is going to be q squared over 4 plus p cubed over 27 is greater than 0. With this, we're going to have one real solution and two complex solutions, okay? The second case is going to be where q squared over 4 plus p cubed over 27 is equal to 0. Here we are going to have two real solutions where it's 3 real overall, and 2 are repeated, right? So that would be for like a cubic. If you had on the plane here where it just touches right here, it's going to have, so this factor would be something squared, it's a repeated root, and then here would just be single. And then the last case, case number 3, that's going to be if we have q squared over 4 plus p cubed over 27 is less than 0. And with this, we're going to get 3 real solutions, and these are all distinct, all different values. Now I'm just gonna show over here what these expressions are going to be if you if you simplify them. So we all know that overall x is going to be just y minus b over 3a, okay? But we're gonna show the solutions for y, and then basically you can just get x from this. But from here, so we're going to have, I'm just going to do y sub r for real. This is just going to be equal to, u plus v. Also another thing, you can, if you have u, for example, let's say when you have the positive inside the cube root, negative q over 2 plus square root of blah blah blah, whatever. If you have that, then v is going to be equal to negative p over 3u. This is just another thing to kind of reference back. You can find u directly. Sometimes it's good to just work with the both of the cube roots all entirely expanded together in their sum, but that's just something to keep in mind. And then your complex solutions, you're going to have, I'm going to do y sub c. This is going to be equal to u. I'm going to represent these in polar form. E to the plus or minus 2I pi over 3 plus v to the e minus plus 2I pi over 3 So basically this is just accounting for the cube roots of unity, right? Because if you have cube root of 1, this is going to be equal to 1, and negative 1 over 2 plus or minus root 3 over 2i, and that's what these are basically. But what you're going to find, normally you would multiply in the entire cube roots by either one of them. Here we have a sum, and so you have the cases of using multiplying by negative 1 over 2 plus root 3 over 2i, or all by negative 1 over 2 minus root 3 over 2i, and then the other one is swapping them, like shown here. And yeah, you're going to see that the only valid complex solutions are when you swap them out. So like here, if we have u, this is going to be like negative 1 over 2 times negative 1 over 2 plus root 3 over 2i, and then this one is just going to be negative 1 over 2 minus root 3 over 2i, and then you just swap them basically. So that's what we have here. We're going to see, this one you can kind of already gauge. The rest we're going to see more in detail where they come from, simplified. We have over here where it's equal to 0, there's 2 real solutions. We're going to get, I'm going to do y1. This is going to be equal to 2u, because in this case, if you think about it, in the square roots inside the formula, they're both going to be 0. So all that you have is just the starting part, the cube root of negative q over 2. And those are going to be both the same for starting for u and v. So basically, you can just take u, so 2 times u. And then the other 2 solutions, y2 and 3, basically there's overall 3, fundamental theorem of algebra. This is going to be negative u. And basically, the way to get this, I'm just going to show it quickly. So if you have negative 1 over 2 minus root 3 over 2i times u, and then plus negative 1 over 2 plus root 3 over 2i. This would normally be times v, but here u is going to be equal to v, since the discriminant is 0, so we're just going to do times u again. And when you expand, you're basically going to get negative 2u over 2 plus I root 3 over 2 minus root 3 over 2. So basically, the imaginary part is going to cancel out. These 2's are going to cancel out. You're going to get negative u. All right. So yeah, that's just basically where that comes from, simplified. And then here, for all three real solutions that are distinct, so I'm just going to do y sub r to include all of them. But anyway, so it's going to be 2 times the cube root of, let's see, this is going to be the magnitude of the complex inside of, we're going to just use u over here. It would be, they're going to simplify out, and then times cosine of theta, the basically the argument of the complex inside of u. These things are going to be plus or minus. With cosine, it's absolute, so theta of u over 3 plus 2 pi n over 3, where you have n is equal to 0, 1, and 2. Okay, now this might seem like it's coming out of nowhere. We're going to see more in depth on how this is going to work with when I talk about the case where, yeah, we have 3 distinct real solutions. Just a quick note over here. There's actually a shortcut that it's somewhat mentioned as a property of the depressed cubic, but not really stated or used to literally find the depressed cubic. Everyone's always like, substitute y minus b over 3a and do all the autopilot algebra, and then you'll get to the depressed cubic. But basically, what you're going to find is that if we have, I'm going to use function notation here, but if we have f of x is equal to ax cubed plus bx squared plus cx plus d equal to 0, set it equal to 0 basically, what we're going to see, first, again, we're going to divide by a, so then we're going to get x cubed plus b over a x squared plus c over ax plus d over a, which is equal to 0. What we're going to get is, after depressing it, this can be represented still in terms of x as x plus b over 3a cubed plus the first derivative at the inflection point, negative b over 3a, times x plus b over 3a, and then plus the function, just the function itself at the inflection point, negative b over 3a equals 0. This one, you can find that this would be the derivative in the second term here for that coefficient, just by basically, I found it just through messing around on Desmos, but also double check that if you find just the normal first derivative with this negative b over 3 at the inflection point, it's going to be the same expression as p over here. And so from here, already you're going to solve for x plus b over 3a, and then again you just undo the shift by subtracting b over 3 at the end. I'm going to use this for the rest of the examples just because it's a lot quicker. We don't really need to focus that much on depressing the cubic. It's more the rest of the solving afterwards. Okay, so for our first example, we're going to have x cubed minus 6x squared minus 3x minus 104 is equal to 0. Now, I'm just going to do this on the side. what we're going to have is, so negative b over 3a. You check this, this is just going to be 2. The derivative at x equals 2 is going to be equal to negative 15. And then so that function at 2 is just going to be negative 126. So we're just going to keep that here. So now this is there's already a leading coefficient of 1, so we can already put it into its depressed form, where we have x minus 2 cubed minus 15 x minus 2 minus 126 is equal to 0. So we're going to get x minus 2 is equal to u plus v. And now, so just the pre-processing here, we're going to get u is equal to the cube root. I'm going to simplify things here already. We're going to have basically 63 minus, so we're going to have 3600. This is actually going to simplify to a nice perfect square. You can tell that this example was well thought out. Minus 62 squared, and yeah, basically going to cancel out here. Then we're going to get 63 minus 62, which is just cube root of 1, which is just 1. Okay, and then I'm gonna find v using the fact that that's negative p over 3u. So that's just going to be 15 over 3 by 1, or 15 over 3, which is just 5. So then, yeah, we get x minus 2 is equal to 1 plus 5, and we equal to 6. And then I'm going to put this as x1 for our first. This is our real solution, because we saw here that the discriminant is positive. So we're going to have two complex solutions we're going to look at after. This is going to be 6 plus 2, which is 8. Now grab the rectangle. So 8, that's our real solution. Now, for our complex solutions, we're going to have x2 is going to be equal to negative 1 over 2. Oops, negative 1 over 2 plus root 3 over 2i times 1, so that's just times itself, plus negative 1 over 2 minus root 3 over 2i times 5. And so this is eventually, oh yeah, and then, sorry, and then plus 2 basically at the end. This is going to simplify. This is going to simplify to be negative 3 minus 2 root 3i, and then plus 2. Add the real parts. We're going to get that x2 is equal to negative 1 minus 2 root 3i. Okay. Then for x3, I'm going to use the fact that these are going to be conjugates. The complex solutions always come as a form of conjugate, so this is just going to be the conjugate of x2, which is just going to be negative 1 plus 2 root 3i. So now we have all of our solutions. Oops. We have all of our solutions here. Okay. So that's the example where the discriminant is greater than 0. You have one real solution and then two complex. Now we're going to have an example where the discriminant is equal to 0. So one of our real solutions is going to be repeated. So what we're going to have, we're going to have is 2x cubed plus 16x squared plus 10x minus 100 equal to 0. Divide everything by 2 because we want a leading coefficient of 1. So we're going to get x cubed plus 8x squared plus 5x minus 50 is equal to 0. Once again, I'm going to write down in the corner here. So negative b over 3a is going to simplify to be negative 8 over 3. Then we're going to have dy over dx, first derivative at x equals negative 8 over 3. 8 over 3. This is going to be negative 49 over 3. And then y at negative 8 over 3. This is going to be negative 686 over 27. Alright, so we're going to use those here. I'm going to reduce to depressed cubic now. So we're going to have x plus 8 over 3. X plus 8 over 3 cubed minus 49 over 3 x plus 8 over 3 and then minus 686 over 27 is equal to 0. So we're going to solve for x plus 8 over 3. That's just going to be, the discriminant is equal to 0. So 2u, u and v are the same. It's just going to be 2 times the quantity. Okay. So solving for u, going to be simplified again. We're going to have the cube root of 343 over 27 plus the square root of, this is going to be 117,649 over 729 minus itself 117,649 over 729. So this is where we get it equal to 0 right here. I just wanted to show this part here. So these guys are going to cancel out. We're going to get 0. And then u is going to be equal to the cube root of 343 over 27, which is just going to be equal to 7 over 3. So then we're going to have that x plus 8 over 3 is equal 2 times 7 over 3. I'm just going to write it down. That's 14 over 3. X is going to be equal to 14 over 3 minus 8 over 3. Then we're going to get 14 minus 8. That's going to be 6 over 3. That's just going to be equal to 2. Put x1 here actually. So this is our single real solution. Okay. Single real solution. Now for the repeated solutions, again, that just basically comes from the cube roots of unity part, just that the imaginary parts cancel out. You already saw that. I'm just going to put it into negative u. So x 2 and 3 is going to be equal to negative u. So that's just going to be negative 7 over 3. Negative 7 over 3 minus 8 over 3. And so this is going to simplify to 15, negative 15 over 3. So this is just going to be equal to 5. Nice and simple. So these are the repeated solutions. Repeated solutions. Let me just box this in. And there we go. So that's for this discriminant case where the discriminant is equal to 0. The final one we're going to have is where the discriminant is less than 0. So we're going to have to be dealing with complex numbers. Okay, when you have all three real and distinct roots, you're going to have to deal with complex numbers in the process, even though the results are going to be real. It's another reason why it's not really taught. So we're going to have here x cubed plus 12x squared plus 42x plus 36 is equal to 0. We're going to check negative b over 3a, our inflection point. This is going to be negative 4. Then if you check the derivative at the inflection point at x is equal to negative 4, this is going to be equal to negative 6. And then if we check y at negative 4, this is going to be equal to negative 4. Okay. Alright, so now we can put into depressed cubic. We're going to have x plus 4 cubed minus 6x plus 4 minus 4 is equal to 0. Alright, so now I'm not going to use the shorthand formula with the cosine and stuff like that because I need to show where this comes from. But if you want to, you can feel free to kind of learn to memorize it or whatever. But it all just comes from the cases of u plus v. But anyways, so I'm gonna do it just from u plus v straight up here. So we're gonna have x plus 4 is equal to u plus v. So u is going to be the cube root, again simplified 2 plus square root of negative 4, and so u is just going to be equal, so yeah, the cube root of, this is going to factor to 2 and then I, so 2 plus 2i. And now what we're going to actually want to do is convert this into polar form. So we're going to have u is equal to the cube root of magnitude here is going to be root 8, or the radius basically, going to be root 8 cosine of, you're going to get pi over 4 plus I sine of pi over 4. Okay, all under the cube root. Now, there's a reason why I did a video on de Moivre's theorem before, some other stuff like, and complex numbers in general. Well, we can use de Moivre's theorem here. It's basically to the power of 1 over 3, and simplify this polar form. We're going to get u is equal to, so root 8, the cube root of root 8, that's just going to be root 2. We're going to have cosine pi over 4 over 3, that's going to be pi over 4 times 3, which is pi over 12 plus I sine of pi over 12. Now we're also going to solve for v. We can start from over here. This is just going to be direct opposite. You could obviously do minus p over 3u, which is the reciprocal. It's going to be perhaps the conjugate. So anyways, v is just going to be the cube root of, sorry, 2 minus 2 minus 2i now. In polar form, going to be the same thing again, only differs by minus sign. We're going to have root 8 cosine pi over 4 minus I sine pi over 4. Okay. All under the cube root. Then here, we're going to use De Moivre's theorem. First of all, the magnitude just gets cube rooted normally. We're going to get root 2. Divide the angle by 3. Cosine pi over 12 minus I sine pi over 12. Okay. So now, when we add these up, right, x plus 4 is going to be equal to root 2 cosine pi over 12, and then plus root 2 I sine pi over 12, and then plus root 2 cosine pi over 12 minus root 2 I sine pi over 12. So yeah, we can see here the imaginary part, the imaginary component is going to cancel out. So then we're going to get exactly 2 root 2 cosine. We're going to have to include the periodicity of these solutions, because in normal formula there's only one area to get started. Here we're going to have cosine of pi over 12 plus 2 pi n over 3, right? So this was technically here from the start. I just like to include it on the last part, the last line where we get our solutions. This was also divided by 3. And then plus 4. So it's going to be for n is equal to 0, 1, and 2. So pi over 12 just itself, then pi over 12 plus 2 pi over 3, and then pi over 12 plus 4 pi over 3. After simplifying these, we're going to get x is equal to -6, then -3 plus or minus root 3. And those are all of these solutions. So this is my go at explaining the cubic formula. It is very interesting and perhaps maybe not useful in the grand scheme of things when you have approximations and stuff for applied sciences, but still very nice for getting exact values. It has a very elegant solution if you are comfortable with complex numbers and the such. And yeah, the three cases here with the discriminant just gave some examples. So I hope you enjoyed this video. I hope this was useful and interesting to you. Next video, I'm probably gonna cover the quartic formula. Yes, there is a quartic formula. But yeah, stay tuned for that. Click like and subscribe, and I'll see you next video.